So then I welcome you all to the second lecture in Parallel and Distributed Computing in summer 2024. This lecture is recorded, so please, if you're very welcome to always comment something, but take care of what you are saying. It may be you can't take it away later. Yeah, so today we continue a little bit with, I should make an announcement, another announcement before. So this course includes an exercise, homework, that you have to do at home and you have to present in order to pass the entire course. We will introduce this exercise a little bit later during the exercise class that follows the lecture class. And not today, because we have to introduce a little bit programming first, and then when we are on the right level, we introduce the class, and then you will have until the end of the semester to actually prepare your homework and do the parallel programming. So you can do it here, a little bit together, and you may also do it at home, but this homework is coming, so we'll have a homework that you have to pass, and then we'll have a written exam that we have to pass. So for the written exam, of course, it's very important. By the way, there is no drinking in this room, because there's too much computers here. Yeah. And by the way, as I recognize, there's also no putting anything on computers. This strange thing here is in order for when you anyway put something on the computer, it's at least not on the cooling stripes. Yeah. That still doesn't mean that now you're free to put something onto it, okay? So we have to behave here, otherwise we are thrown out. Okay, so now this is also all on the record. Okay, so for the exam, of course, it's also important, besides some programming tasks, to know about basic terms and concepts, and some of them we'll introduce today. So we go back to the multiple instruction and multiple data classification for computers. We'll talk about networks, and then we talk about scaling in parallel programming, if we get everything that I wanted to do today. And we start with a classification of parallel computers. Parallel computers. So I'm trying to draw a small picture. So very in general, we have a parallel system. So, and these are classified as, if you listened to me last time, there is single instruction, multiple data, which of course you can specify, branch out more, but today we'll look specifically at the branch of multiple instruction, multiple data. So these systems can be very diverse. So they can be classified in distributed memory systems, and shared memory systems. So, for example, I guess nowadays even your phone has multiple cores, right? I guess so, yeah. So is this a shared or distributed memory system? Is a phone a shared or? Well, if you count the cloud, then it's probably a distributed. No, your phone itself is of course shared memory. Yeah? So you have multiple cores in your processor. Usually it will be probably an ARM processor with multiple cores, but they have one memory in the system, so they share their memory. Okay, and the distributed memory systems, there are several possibilities. So something that's called MPP, and I just recognize, I don't know what this is actually the abbreviation for. Then there is networks of workstations, and there's something that we call cluster. Okay, I specify the names for this in a minute. So the shared memory system, we've already said last time. So now I can check whether you listen to me. I just try to say that there is no drinking in this room. Yeah. He arrived late. Okay, yeah. Okay, so what is UMA standing for? We had this last time. Uniform memory access, right? Then we have, of course, non-uniform, NUMA. And NUMA, we already specified that we had CC, cache, that always happens here, cache coherent NUMA. And then there is a non-cache coherent NUMA. And then there is something that sounds a bit crazy that's called COMA. I wouldn't call my computer is in coma, okay. Doesn't sound so well. COMA is cache-only memory access. Okay, I'll write down a few of these. This MPP, and I have to apologize, I should have looked it up, but yesterday when I wrote this, it did not occur to me, but this is not, I don't know what the second P is actually standing for. I can only tell you what it means. It's a massive parallel something. So it's a massive parallel system. It should actually be MPS. I don't know why it's MPP. Sorry. So massive parallel system. This is very specialized, so it's hardware that has been designed for this system, and usually also software designed for this system. So it uses a unified operating system. Usually designed for this machine. Or for machines of this type, and this is where you have the really big computers. So the big supercomputers, these are these MPP systems. So something that's much more simple and down to the earth is what they call now, probably because you can almost use it right now. Yeah? So if you don't have anything else, this is just network of workstations. Network of workstations. So this is a loosely coupled system, if you will. What I'm doing? Loosely. A loosely connected group of individual computers. So this is like the ones you are sitting in front of. We do all. So unfortunately, I now have to switch to the next page. Individual computers on standard hardware. Say this is standard, whatever this means. So what you can buy from the shelf, I mean, yeah. Okay, so this is something that we could realize here. Yeah? So you have these computers, there is somewhere there's a hub where they are connected, and so you could use your, I heard you talking about IP address, and I don't know whether they all have a hot IP address or whether they are in a subnet. I don't know. Yeah, it doesn't.
It's external. We tested it.
You tested it already. Yeah. So everything here has their own. So we can actually increase it to your computer at home because we have hot email. What nonsense I'm talking. We have. External, we have hot IP addresses, so you can individually connect to each of these computers. But even if we had local ones, yeah, so we could interact between these computers and let them work together. This would be a network of workstations we call now, and then there is the thing that is called a cluster. This is something in between these two extremes. Between the very high performance computers, the very big expensive machines, and the very simple network of workstations. This would be a network of computers with, say, a high performance. It's still more or less off the shelf, but it's a high performance network. And they have, in this, they still have separate instances of the operating system. So it's kind of a little bit in between. Usually these things are located, say, geometrically close together. So you have you have a rack, yeah, where you can put these, what is this, plates, yeah, where you have the compute nodes in plates, and then they have a network connection in it, but the network connection is in the same rack, yeah, so that they are physically very close to each other, and there is usually no screens and no keyboard, yeah, connected to these things. They are all in a rack. They are physically close to each other, so that the network can be implemented, can be fast, but they are still individual compute nodes, so individual processors, and they may also have individual hard drives, or may not have. So these are the distributed memory systems and the shared memory systems, which we already named was the CC NUMA. The CC NUMA is the cache coherent non-uniform a memory access. Then NCC NUMA is the non-cache coherent. So, I mean, what does it mean? One is cache coherent and the other one is not cache coherent. What would it mean that cache is coherent? So it means you have two cores, yeah, working together in a common memory, in a shared memory. One accesses the memory. So one accesses the memory first, does something to the memory, and then the other one is accessing the memory. And when the action taken by the first processor is still in the cache, then they would be, and the other one takes something or writes something to the cache, so there is a conflict, obviously. Yeah, because the cache in the one processor and the memory outside, they are not in the same state. So, because there would be two caches for the two cores, the two caches could point in the same location in memory, but could not be identical. Yeah. So, and this is what happens in the non-cache coherent NUMA, and the cache coherent is something that is a mechanism that takes care that this is not happening. So, for example, by setting a bit that this cache line is dirty, so it has been touched. Yeah. If some other processor is trying to touch the same cache line, it sees, okay, so this has been touched. I cannot access this. I have to access it through the other cache, or I have to update this. Yeah, this would be cache coherent. So, and then we have the comma thing that is called cache only memory access. Translation. Okay, so what did you translate? Cache. Ah, so. Okay, I'm a little bit in the yes. I think I roughly introduced what cache is last time, but I still assume. Yeah. Okay, but I still assume that you have some background in basic hardware. Yeah, otherwise no, not at all. Okay. Yeah, so yeah, because we are now talking about the little bit more advanced stuff. Okay, we'll talk about processors that we have later, not today. Now I just wanted to draw a small picture. I hope conveys the meaning of Kuma and NUMA. Say we have here, so the line is supposed to be a network. And here we have a cache that is connected to a processor like the core. And no, there's not a network. This is I want to say this is the bus. So here you have your memory, and the memory needs to be connected to a directory, which, okay, we physically could draw inside the cache because it's probably physically in the cache, but what is meant here, the cache is a memory, is a small memory that keeps a copy of the big memory, yeah, and it has to store, of course, also the position where it has been taking this cache lines from, and this is located in the directory. Yeah, so this is okay. So we have the actual data, and we have, of course, the position of this data. So, and I need a little bit more space than maybe I draw these two things below each other. That would be probably better. So say we have another computer. We have another computer with cache and with memory. And there is, of course, another directory. And there is a bus. So, and now you want to, so you see, this is distributed memory, yeah? So the left compute node has its own memory and its own cache, and the right compute node has also its own memory. And the two now should exchange data. And what happens in NUMA is that the data that is located in the other part of the memory goes into the cache, and the design feature here is that the datum as the singular of data, the datum has a fixed home. Yeah, so so the datum is still in the other domain, or in the domain of the other processor, while it is taken care of. This is what happens in a NUMA machine. And in a COMA machine is more complicated. So let me give some space. So COMA machine looks like this. We still have this cache. We have a processor connected to the cache. And then there's also a directory, and there is something else which is kind of similar, which we call a tag. So the memory is tagged, and then there is the memory. And then we have another instance, or another compute node, where we also have a directory, and we also have a tag.
Professor,
Yeah.
what is the directory?
Where the directory is.
No,
You mean physically?
I mean, what is it? Is it like
Yeah, it's the... Yes, what is it? Right. It is saying that you have your complete memory, right?
Yeah.
And everything there has an address. Yeah. So if you want to, the directory in the sense you want to send something to Clausthal. Yeah. So if you want to send something to Clausthal, you need to have a directory, like in the old days you have a book where you have the postcode for this. Yeah, so this is what we mean by directory, because this is not a fixed directory in the sense, because we have our cache lines, yeah, and our cache lines have to be linked to a specific place in the memory. Yeah, so you have to remember in the directory says, because you have more than one cache line. Yeah, so you have several cache lines, and the directory says this cache line goes there in memory.
So, if I transfer something from the memory to the cache, it will add this line on the directory. Or is
Yes,
it
so it will add. Right. So if this is a new, so you are accessing new data that you previously did not access. So then it has to read it from the memory and puts it into the cache. Yeah, and then it has to remember where it's coming from. So then the idea is that you do not send it backward and forward all the time, because this is the point of the cache.
Yeah.
So you do all your work. You do as much work as you can in this in the cache, yeah. But time and again you have to send it back. So you need to know. You need to know where it is and that you already have it in cache, for example.
Okay.
Yeah. So because if you so you have right, so it has to be clear. So you first look in the directory whether you have it in your cache. Yeah, then you access it in the cache, and if it's not in the directory, then you have to read it in the cache and access it.
In case of NUMA, if you transfer something from take out from the memory and put like another computers or
Yeah.
cache.
So you're confused that the directory is here connected to the memory. I've drawn the picture as it was in the book, and I have to agree that it could be a little bit confusing, because the directory is physically connected to the cache. Yeah, it's not in the main memory. Yeah, maybe there's a little bit confusing in this picture.
It wasn't my question.
Yeah.
I need to, when I make this transfer, I need to put in the home of the directory that it was transferred for the.
Yeah, so you need to know that it also came from outside.
So I need to put like in both of the computers the address of the memory, like in both directories.
In
I
those.
mean, not computer scores.
So you have to put it. So you have to put it now here in this case on the left computer in this directory. You have to put it that it is that it's already there, because otherwise you would have to. Because you have the directory is something that you can read quickly. You must need quickly. Therefore, you need to know locally that you got it from somewhere else.
I got it.
Okay, so the question is whether in the other directory you have to remember that it was taken and give it a dirty bit. Yeah. So, but this is now because this is now not specified whether this is cache coherent or not cache coherent. So if it's cache coherent, then you have to take it again, saying that it is dirty or not dirty. But you see, this is a grand, say, concept. They do not necessarily all work the same. Yeah. So I cannot. I can't tell you how this is done specifically in that machine, because these machines work differently. They are very complex. So this is more like a concept, and in the realization in the machines that you can actually buy are always specific. Please.
Yeah, is the directory the same as a page table?
Yeah, so that would be page table. Yeah.
Okay.
Yeah. So, but then here in the comma there is something else that is called a tag. And the tag is something that we need for all memory now. So the directory only takes care about the data that is in the cache or probably not in the cache. But the tag is something that now we have to put to all memory that we have, because what this does when it's transferring data is it is taking. So if the left node wants to have something that is in the memory of the right computer. So what it then does, it transfers the datum to its own memory. Yeah. The position. So that this means that the position of a datum is not fixed. And because the position of a datum is not fixed, we have somehow to remember what this datum actually means, and this is done by the tag. Yeah? So the tag is saying, so this is actually for you, or for this position. So remember there are some posts. You're in a post office. There are some shelves for the different people. Yeah. So and there's written here's Professor Geier, here's Dr. Schönherr, and so on. And now you can put the post for me there. So then I go there, pick up the post, open it, and I assume that it's mine. Yeah? So it was for me because somebody sorted it like this. When it's lying on the table, I need the name. Yeah? So whether it's for me or not for me. So now, because they are not ordered in these boxes, the datum, every datum has to have its name saying what it actually means, yeah, because it can be transferred. So the datum here, the datum migrates wherever it is needed, which potentially also means that it's doubles. So this is something relatively complicated and also not, in my belief, it's not necessarily that common. And this is also, all of this is not necessarily completely fixed, that the machine only works like this. This is more like you should think about Platonic, concepts. Yeah, so there's a clear comma and a clear numa, but you can also, you can always add a tag to something and simulate one computer on the other. Yeah, that's also possible. So no, what I wanted to say is that in the realization of these machines, there are variations on these principles, yeah, so they are not 100% like this all the time. Okay, yeah. So why are we studying this in the first place? So if you wonder now, is of course that understanding how your machine is built, which is actually not that easy, because probably, especially when we talk about caches, because probably the manufacturer doesn't tell you how it's built. So understanding the architecture of your computer, I'm very sorry that I cannot stop this, of your computer is of course essential if you want to have an efficient program. Sorry. So let's consider an example. So, for example, we have to deal with caches a lot nowadays, and this is in relation to what I said last time about the increase in compute power. Yeah, so memory access grows much slower than other things. So this means that nowadays, or in future, more and more, the performance of computers depend on their caches. And so also the performance of the programs we write depends on how well we understand how the cache works. So, say caches are accessed in form of cache lines. What do I mean by cache line? I used the word, but I did not explain it. So cache lines of fixed size. So what is a cache line? But you have heard the word cache line, yeah? No? Who has never heard the word cache line? Okay, what does the translation say to cache line? How is cache line in Chinese? Well, a cache line, so you want to access okay, so you want to read a single number, say an integer. How many bytes does an integer has usually? 1 byte? 4 bytes, yeah, 4 bytes. Yeah, so you want to read 4 bytes somewhere in some place in memory, which you have not yet read into the cache. So the first time you do is you just started your computer and you read this 4 bytes. So what does the cache do? Does it read the 4 bytes? Well, could depend on your computer. So what computer do you have? Say you have a 46 bit computer. I say 64. 46, yeah, sorry, 64. 64. So how many bytes are these? 8, yeah, it's 8, yeah. So, or say, okay, so this is the processor, but then you have a data bus. So the data bus has a certain width. Say the width is, I don't know what it, okay, I have to admit I don't know what usually the width is, but say it's 256 bit, yeah. So this is, the bus. This is probably why it's called a bus. Yeah, if you're coming by the bus doesn't care whether it's empty or it's full. There's always a bus going backward and forward. So you cannot read a single byte. But you can also not read 4 bytes. Because you have to read the width of your bus. Yeah, so always this length of a line, this is read together. So this is the minimal size of what you can actually read, yeah, and you're not saving any energy. So if a bus goes someplace, you're not saving any energy if you just take one. If there's just one guy coming, yeah, this takes the same amount of fuel in principle as if many are coming. And this is the same thing here. So these things are read in fixed size. So first of all, there are two things. First thing is you have a width of a bus, so you can only access memory in these fixed chunks. And the other thing is you're assuming that if you access data in one place, that you will then in future probably access data that is close to that data that you have just read. So what the bus does, it goes there, takes everybody there, and the good thing is there will be a copy, right? So you will clone the people, so they will still be in the old place. So now you have to. Now this is what you have to know. You read something. You want just to read one thing, but you read also its neighborhood. And this comes in these fixed size, in lines of fixed size. And then you want, of course, you want to use this. So for example, you want to avoid cache misses. So what is a cache miss? What's a cache miss?
It's a mess.
It's a mess if you have cache misses.
Yeah, it's a mess, it's one.
Yeah, so no, a cache miss is whenever you want to read a data. So I was talking about the directory or the, what was the name that you used? Page table, yeah. So you look in your directory first if you have this place in memory already in your cache, and every time that you don't find it, it's called a cache miss. Because what do you have to do with a cache miss? You actually have to go out and take the stuff out of memory, yeah. And you have to remember this is expensive. Yeah. By the way, I mean, like, what is, just think about this. What's the fastest you can go? You can go with the speed of light, right? Yeah. So now, what is the clock frequency of a computer? It's in the range of 1 gigahertz. So how far can you move in 1 gigahertz? So 1 gigahertz in one billionth of a second. How far do you go in 1 billionth of a second? 30 centimeters. Yeah. So this makes access. So you can imagine. You look at your computer. Yeah. So maybe the memory is. So they try. Actually, the memory in modern computers, the memory chips go closer and closer and closer to the processor. Yeah? And if you look at the GPU, the memory is all around, directly built, outside, yeah, as short as possible, yeah, to reduce this distance, because you cannot move because you see it's expensive. In 1 gigahertz, you cannot go further than 30 centimeters. So to avoid cache misses, you want to use the fact that you have these cache lines. And this you do by processing data sequentially. Sequentially, I mean with a maybe I don't write sequentially, but continuously. Continuously. Okay, example. So later we'll have in the exercise we'll little bit introduce C++. Or so if I write in C style a program like this, so there would be a loop over I. Say this is an LX I++. So this is a loop over some I, and then there is another loop over some j coming from 0. J is smaller than Ly, j plus plus. So, and now I'm doing something like this. I have something that I call data 1, and this is indexed by I plus Lx times j, and this is just some function, we don't care, of I and j. And I do something else, data 2, which is j plus Ly times I is a function, is again the same function, which what it does is not very important now. And then I have to put a semicolon, and then we'll close these two brackets. So now it's your turn. It's your turn telling me which of the two is a good idea and which of the two is a bad idea, and why. Okay, it has of course to do with cache line. If we think, so when I learned programming 30 years ago, they would say that there's no difference between this. Yeah, without cache there's no difference, right? So now we have cache.
I got the point. It's like one of these two, the cache is gonna jump.
Yeah.
Like the entire length of the.
Yeah. So say these Lx and Ly are larger than one cache line. Yeah.
Yeah. Let's say like the second one is worse.
The second one is worse. So why is the second one worse?
No, sorry, it's the first.
The first one is worse. So why is the first one worse? So who? Okay, say you introduced it as a negative question. Now I ask you, who is for the first is worse? Hands, please. They will not be recorded. Just hand, please. Who thinks that the first is worse? Who thinks that the second is worse?
I just have a question.
Please.
So this I plus Lx times j, or this type of array, is a way to write in one dimension?
Yeah. No, they are. This is. Yeah. So this is of course one. Okay, they have only one index. So this is one-dimensional. There's no comma in between. Yeah. The one is I plus Lx times j. Okay. So if you in nice C++ style, you have of course to draw asterisks, right? So the one address is I plus Lx times j, and the other address is j plus Ly times I. So, okay.
I think the first one is worse.
The first one is worse. Why is the first one worse?
Because the second loop is the one that it makes continuously, I guess, and it jumps like Lx every time.
So, yeah, so the inner loop is the one that is processing the fastest. Yeah? So this is the fast loop. The fast loop is the j loop. Yeah? So it jumps by Lx in every step. Yeah? So if this is longer than one cache line, so it has to read a new cache line every time, or it has to write. It has to write a new cache line every time.
Yeah.
So in the second case, we are actually proceeding continuously. Yeah? So it can write these, it can fill up a cache line and write it only then. Yeah? So this means this here is the one that is this is the one that is bad, and this one is the one that is good. Okay. This brings us to the next topic of today. Or is there any questions regarding this nomenclature? Because otherwise we come to networks.
I'm sorry, just.
Yeah, please.
I get what you just mentioned. So the second loop was a better one because Ly is the fastest loop. So
No,
Ly,
J is fast.
Sorry, Lj is faster.
No, not Lj is the length. So
J
there is no Lj. Sorry, you mean, or what you mean? The loop J, the loop over J.
is the fastest.
Yeah, the second is the fastest because it goes over J. No, because it's No, okay. Why is the second the fastest? The second is the fastest because it's internal. Yeah, so it does an entire loop over J before it increments I by ones. Yeah, yeah, and therefore, this is the J is continuous, and so this here is a continuous increase, and this here would be jumping.
Okay.
Yeah. Okay. Any other questions?
Is there any way to avoid this, or to get around?
Yeah, there is a way to avoid this here by taking the second way of doing it. So it's important. Sometimes you have more than one constraints, and sometimes you cannot. Sometimes it's not possible to avoid it. Yeah. So, but usually you can mitigate it. There's always a way to make it worse. Yeah? There's not always a way to make it better. Okay, we are talking about networks, and here again we have to introduce a lot of terms. So first let me introduce what by a network is a graph that is built from so-called nodes, and in our case this would be compute nodes, and they are connected by connections which we call edges in graph theory. Connections, so this is an edges. So we'll draw a network like this. Yeah, so there are nodes and they are somehow connected in one way or the other. Now we have to introduce a few terms. This is, for example, the distance between nodes. So what do we mean by the distance? So how do I say that? What is the distance between that? Can I actually see this? Probably not very well. So what is the distance between this node and that node? Yeah, and don't tell me it's okay, whatever. It's on my screen. It's 2 centimeters. On this screen here, it's probably more like 20 centimeters. Yeah, so that's not what we mean. We mean the distance in terms of how many edges you have to you have to pass through to actually get from one to the other. Now, there may be different ways to go to the same place. Yeah. So, for example, you can ask the question: so how far is it from here to Hanover? And you say it's. You could say, okay, it's 70 kilometers. But wait, you could also say we go the other way around, and then it's, I don't know, a little bit more. Yeah. So what we mean by what we usually mean by the distance is the shortest way to get somewhere, right? So this is, therefore we call this the shortest path. By the way, in a network, they don't necessarily take the shortest path. Do you know why the internet was actually invented?
Where?
No, why, not where. I mean the ARPANET, the one. I don't mean the World Wide Web. I mean the internet. The internet was before there was World Wide Web. You know, the internet is World Wide Web happened in my lifetime. Internet is much older. So web browsers and these things. This is something relatively new. The internet is much older. Internet. Internet was the idea to prevent. This is a Cold War idea. Yeah. So in comparison to the usual phone lines, you build a network that doesn't have a center. So when an atomic bomb drops somewhere, yeah. So for example, you could imagine that in America, yeah. So World Wide Web, the internet that we know today actually comes from Switzerland, but the original ARPANET that actually comes from America. And what could happen there is, for example, atomic bombs drop in the middle of America, so everything in between is cut off. But there is still one possible connection because it does not have a center, it does not have a usual line. It would simply go, from New York to California. It may pass through Africa, yeah, New Zealand, the other way around, and arrive because when everything in between would be cut out. Yeah. So as long as there is a path, you can pass. So this is security measure. And then they discovered that you could also distribute pornography with it, and then yeah. So it's the shortest path in number of edges. I will now frequently use this hash operator, meaning that this is the number of things. Okay. So then we have a degree of a network. The degree of a network is the largest number of edges at a node. It is not necessarily so that each node would have the same number of edges starting at this point. So we take the largest number. So for example, what degree would this network up here have? Yeah, it would have 2 because all the nodes have the same number of connections, and all of them have 2. So, and then we also have a diameter. We have a diameter of a network. Diameter is the largest distance between nodes, or between 2 nodes. Okay, so it's the question. So what is the furthest distance, yeah, that the network has to support? Okay, let's look at some of these examples. How does it work? Yeah. So examples of this. Conceptually, the simplest network is the fully connected network. It's also the one that is the most difficult to build. So, fully connected network. If we go back to the example of 4 nodes, then a fully connected network would simply connect all the nodes to each other. Now say we have n nodes in this fully connected network, so then what would be the diameter? So diameter is the furthest distance you have to go between 2 nodes. Yeah? So because they are all connected, yeah, there would be a diameter of 1. Yeah? So what is the degree? Well, yeah, okay. Okay, you look at the picture. No, in general.
Oh,
N minus 1. N minus 1. Yeah. And then the number of connections. Yeah, so the number of connections, so I guess I give you this, the number of connections is n minus 1 factorial. Does this work here? So we have 1, 2, 3, 4, 5, 6. Yeah, 3 factorial is 6. Yeah, okay. So you know, I did not think, I just took it from my paper. Okay, so this would be a fully connected. Then the simplest network to build would be a linear network. Linear network looks like this. You have your nodes, and then in between you have your links, yeah, your connections. Okay, we'll always also for the other ones I will stop writing this now, but we'll always have n nodes. So the diameter of this what is the diameter? And n minus 1. What is the degree? 2. Okay, why is not 1?
Because in the middle is 2.
Yeah, so there is the large, right, so it's 2. And so the number of connections, this is, it's the, I forgot how this is the word, the Pfostenproblem. What is Pfostenproblem in English again? This is the fence post problem. I don't know. This is a very, very important in computer science. So if you have, well, what are the posts? The posts are the nodes, right? And the fence is the connections. Yeah, it's n minus 1. Yeah, so there's always one piece of fence less than there are connections, unless the fence is closed. And the fence is closed is the next possibility, which we call ring. How's time doing? Okay, ring. So ring, or we call this 1D torus. So that would look like this. So it's the same as linear, only the ends are connected to each other. So the diameter, what does this mean for diameter? N? Really N?
N
Hmm?
Means what?
No.
No, it's
Okay, so like going back to Hanover, if there is if there is some line in between, yeah. So the furthest distance, you could say there is a wall. Say, imagine there would be a time when there would be a wall straight through Germany someplace, yeah, and the only way you could not pass around the wall. So the furthest distance, if you want to go to the other side of the wall, you have to go all the way around the Earth. Yeah? This is why previously, when it's not connected, the diameter would be n-1. Now you can go. If you can go both directions, then it's the question in which way it is closer. So what does it mean?
go all around.
No, you don't want to go all around. You stand somewhere and you can go left or right, and you say, okay, when it's closer left, then I go left. So
n divided by 2.
it's n divided by 2, and it's the lower bound because
Floor. It's because I like it's a function floor.
floor. I did not hear you. Yes. Okay, floor. Right. So degree. Yeah. So these brackets, these mean floor. Yeah. So up there would be ceiling. Right. So this is the degree of this thing is obviously also 2, and the number of connections is n. Yeah, it's wrong on my sheet. Number of connections now is n. So then we have a multidimensional torus, DD torus. So now I have to do a little bit of drawing. Say we have connections like this. Please take, okay, so there are no diagonal connections here, yeah? No diagonal connections. But there are connections going this way, and there would be connections going one connection going that way. Right, so this is a DD torus, so in this case it's a 2D torus. So the diameter of this thing, would be the number of dimensions. Okay, so this is the number of dimensions times n by the root, by the dimensional root, if you will. So n by the power of 1 over d divided by 2, the floor of this and this times d. Okay, and the degree of this is 2d. You see, things can become more complicated. Then there is something called the d-dimensional hypercube. So hypercube. So the hypercube has n. So the number of, because it's a cube, it has n equal to 2 by the power of d nodes. And you can draw this. I mean, in order to draw it, it should not be more than 3-dimensional. Otherwise, it's getting a little bit complicated for drawing it, at least for me. So let's draw a 3-dimensional cube. Well, let's try to draw a three-dimensional cube. Is there something that I need to specify?
The diameter of the torus, what is the exponent?
The exponent
1 over d?
is 1 over d. It's 1 over d. Okay, say, so there's one connection missing. So I cannot draw a 27-dimensional hypercube, but I can draw a 3-dimensional hypercube. Maybe it's then not hyper, but it would be the same thing. So each of these nodes is connected to d of its neighbors. With d neighbors. And I have to go to the next page, I'm sorry. And they are indexed by d bits. So each of the node has its index. Yeah? So they need to have an address, and this is done here by an index. And so we'll call this down here, has the index 0, 0, 0. Yeah? So it's three-dimensional, so it will have 3 bits. For the index, we call this one here 0, 0, 1. This we call 0, 1, 0. And this back here we call 1, 0, 0. Then in this case, this will become 1, 0, 1. This will be 0, 1, 1. This will be 1, 1, 1. And the missing one is 1, 1, 0. Okay, I hope I did this correctly. So these are the addresses of the node in the cube. And now what you should recognize by looking at this is that each of these nodes, or the node index, differs by just 1 bit from those of their neighbors to which they are connected. Neighbors. Okay, I don't know. There was this fun thing with Arnold Schwarzenegger. I learned that if you are a German speaker, you cannot pronounce the word neighbors correctly because they say neighbor. I don't know whether I say neighbor. I did not know this before. So they differ. So for example, if you look at the 0, 1, the 0, 0, 1, yeah. So it's connected to 0, 0, 0. 1 bit, the last bit is different. To 0, 1, 1, 1 bit is different. To 1, 0, 1, 1 bit is different, right? So this tells you that, I mean, here we can draw it on paper and can imagine it, but the same happens for hypercubes in higher dimensions, yeah, where it's difficult to imagine them. But still, the same would hold if you have an index that differs by just 1 bit from your own index. You can access this computer directly over this link. Node index differs from neighbors by, I did not finish my sentence, by 1 bit. So, now the problem with the network is you don't always want to talk to your neighbor, you want to talk to something that is further away. And the question is how to get there. And here the path through such a network is by changing one bit at a time. Change one bit at a time. So, for example, say we want to go here. So, say we want to go from here to there. Yeah. So, how do we get there? I mean, there's of course now several possibilities. Yeah, but we'll take only one of them. So, for example, we can use. No, this is not a good. This is probably not the best color for seeing it. Say, what do we take? This one. So we take this path here first, then we go here, and then we go here. Say, so this is one of the possibilities. Okay, I have the challenge that I cannot keep this in focus while writing. So say we have 0, 0, 0. This is our index. So we change the last bit, 0, 0, 1. Then we change this bit, 0, 1, 0, 1. And then we change the last bit, 1, 1, 1. Yeah, so, okay, I could have taken another path, of course, by changing the other bit here first, so 1, 0, 0, and then changing it. Yeah, but this is how you find from one place to the other. Yeah, you look which bits are different. So you change just this one bit, then you go one further and you do this until you have changed all your bits to the same. So this is how you get where you want to go. So this also implies that we can compute the distance between nodes is the number of bits that are different in the index. So, numbers of bits different in index. There is a word for this. So if anybody studied computer science, actually? No, not really, no. You officially, but only by, okay.
Just in my home uni.
So, but do you know have you heard about Hamming distance? Hamming distance.
Yeah, but
Hamming distance.
so.
Okay, so what we have just discovered, that the distance between the nodes is the Hamming distance of their indices. Yeah? So the Hamming distance what is the word for Hamming distance in Chinese?
It's actually Hamming distance.
Hamming distance.
Yeah.
So Hamming, okay, is the number of non-matching bits into. No, wait. Is the number of non-matching bits in 2 words, okay, in 2 words of same length. So they need to have the same length, otherwise we cannot specify this distance. Yeah, so this is called a Hamming distance. Hamming distance is the distance between data. How many bits you have to change to go from one datum to another datum. And this is exactly what we need to do here. Oh, I messed up with... Oh, let me see. So we are closing in, so I guess I have to do a few things that I wanted to do today, next time. But let's bring this networks here to an end. So the diameter of this is d, and this is the same as saying this is the logarithm, so the base 2 logarithm of n, and the degree of the network is also d, which of course is again the logarithm to base 2 of the number of nodes. Okay, so these were some basic terms on networks. So we have only a few minutes left. Let me, anyway, use this to start with the next we are going to continue this probably later, just as an introduction and a teaser for next time. Parallel programming. So now we want to do parallel programming, and in parallel programming the question is, the idea is we have a problem to solve, and we have machines. We have more than one machine, so we want to use several machines to work together to solve the same problem. And now we would probably hope that this is more efficient, at least more time efficient, so that they get the problem more quickly done. And then I always ask the question, if one bricklayer needs 1 hour to build this column, say, okay, so how fast would 3,600 bricklayers build? Yeah. So, do you think this is true? So you take the 3,600 bricklayers in this room. Everybody has a brick, and then they all get here together and lay and they have 1 second to bring their bricks. Maybe not. Probably not. Yeah. So because there are limiting factors in parallel programming, and there's of course science behind this. And I think because we are now running out of time, I'll go to the equations next time, but let's just start with some limiting factors in parallel programming. Parallel computing. So what is limiting us? So for example, there is data dependencies. Yeah, so there's forced. So what is a data dependency? Yeah. So every bricklayer has a brick. So for example, the one bricklayer that is supposed to lay the brick in 2 meters high, they can only lay this brick if the bricks below this has already been laid. Yeah? So there is dependency on something. And this may force you into sequential the dependency force you to do some things sequentially. And they cannot go in parallel then. Another problem is the startup. So you have to, what is the stuff that you put in between the bricks? The mortar. The mortar, yeah? No, cement is what you do, then you don't need bricks.
We need.
There's mortar. Yeah, that's called, I think it's called.
Mortar is too simple.
Mortar is too simple?
Yes, cement.
Okay, whatever, yeah? Who is a civil engineer here? Yeah, okay. So you think that it's more than mortar?
No, there's cement in mortar.
I think that mortar is the cement. Cement is only a part, in the mortar.
No. Water is a part in the cement.
Not water.
Mortar.
Mortar.
There are several ingredients to mortar. Cement, water.
So it's not
And
water.
sand.
Not water. No, you cannot. Yeah, no. I was not suggesting that you put water in between the bricks.
Water. Okay. Never mind.
Oh my God. Yeah. So you put mortar in between. So you have to mix the mortar. Yeah. So this has to do before you do the bricklaying, and the bricks has to be delivered and so on, right? So there is startup. That takes time, and then there is of course bottlenecks. This is in particular due to shared resources. Bottlenecks. So, for example, if you have one bucket in which you have your mortar, yeah. So in each of the 3,600 bricklayers has to access the same bucket with the mortar, then obviously this would be the problem. So they can be either shared or they can be slow. Access to shared or slow resources. And the other thing is the coordination and communication. So for example, one bricklayer can of course think about himself, herself, how to lay the bricks. If there are several bricklayers, they have to coordinate and communicate to who is laying what brick. And this also leads to the resources required for the management. So the boss that is crying around, you don't stand here, do something else, yeah? Organization. Okay, now since we running out of time, I just give you a teaser for the 2 questions that we are going to answer next time. The question 1 is, how much faster, okay, so they are not interested in us, I hope. And then how much faster can a problem be solved on n cores compared to 1 core? So this is basically the bricklayer example, yeah? So you just want to build this one column. Yeah, and the question is, you take more bricklayers, how much faster can they build this this one brick? And the another question at this one column. The other question which we are going to answer next time is also, so we are not answering these today. The second question would be, how much more work can N cores do instead of 1? Okay. So, first of all, I will now stop the recording. We'll have an exercise, and the exercise is not recorded. Yeah, exercises will be not recorded. And yeah, first let me stop this. Oops.